Okay, stats. Chapter 8 is about distributions of sample means and sample populations, and it's primarily about how normal distributions pop up everywhere and why we talk about them so often and why we can use our tables so frequently. So it's sometimes hard to understand what a population is because it's so big. You know, if everyone's part of the population, say of Weatherford College students, that would be a huge amount. But what if you took a bunch of little populations and like clusters of every classroom at Weatherford College and found some data about them and took their averages and standard sample means and standard deviations and then took each of those clusters and averaged them together to make up eventually the whole population with a bunch of small groups. Statistics such as X-bar, a sample population, are random since their values vary from sample to sample. You could do something like the average height in each classroom, something like that. As such, the average height in each classroom might be different. They have a probability distribution associated with them because they're a random sample. In other words, we can find a mean and standard deviation for all the little groups. And then from that mean for the little groups, we can find some means and standard deviations for the big group based on the little groups. So sampling distribution of a statistic is the probability distribution for all possible values of the statistic computed for a sample of size m. So the only thing that's important about this is we keep all the sample sizes the same size, so they have equal weights. And the sampling distribution of the sample means is the probability distribution of all possible random values of the variable x-bar computed from a sample of size n. So it's basically how the x-bars, how the averages compare. In the past, when we did one big group, we were comparing individuals and how they related to the sample. If we're doing a bunch of clusters, we're comparing how all the averages of the small clusters compare to the average of the overall population. Now, one side effect of this we'll see moving forward. So let's talk about what it is if we already know it's a normal population based on the data. The weight of pennies minted after 1982 are approximately normally distributed with mu equals 2.46 grams and sigma 0.02 grams. So mean is 2.46, standard deviation 0.02. Approximate the sampling distribution of the sample mean by obtaining 200 simple random samples of size n equals 5 from this population. I don't know about you, but taking one random sample of 5, for example here are the weights, and getting 2.479 is not so bad. Doing this 200 times, not pleasant. Thankfully, it's already done for you, and these are the 200 means for our set of data. So the mean of these means is still equal to 2.46. Because it doesn't matter how many pennies are in your group, the mean should still approximate the expected mean. What about the standard deviation according to the chart of this data? If you look at the very lowest and the very highest, all of our means are between 2.435 and 2.485. That's basically within 0.02 on either side. So it's within what looked like a single standard deviation from our problem, which is really unusual for all the data to be within a single standard deviation. And that's because every single one of these, if you took 5 numbers and you found the average, what happens? Well, let's think about this. If I have the numbers 1, 3, 5, 7, and 9, the average there is 5 because they're going by 2, so it's the middle number. And all that would be reported in that number is 5. You wouldn't see the 1 or 9 because in that little group, the 1 and 9 basically weighed each other out and were lost in the mean of my small sample. So what happens here is when you take a small sample and then use it to make a bigger sample, when the numbers weigh each other off, so basically the 9 and the 1 balanced each other, that's never really reported in the mean. You just know that the mean ended up being 5. So the standard deviation of this set ends up being only 0.0086, which is less than half of the standard deviation of the original single penny value. Now, we can do this again. Instead of doing samples of size 5, what happens if we do samples of size 20 and do 200 of them? Now, let's not do this ourselves, but thankfully we have another graph to kind of explain what's happening. So if we do 200 samples of 20, if you look at the distribution here, it is even more tightly packed than the previous one. Because again, when you had a sample of size 5, which we were talking about before, what happens? Well, you have 5 opportunities for the positive side, like the larger numbers and the smaller numbers, to outweigh each other. When you have 20, you have significantly more opportunities to get high numbers and low numbers, which gives you all but guaranteed chances to outweigh each other. If you look at this distribution, everything's between 2.45 and 2.475, so they're even more tightly squeezed than before. In fact, the standard deviation is now only 0.0045. This is about half of what it was even with 5 pennies. So it comes up with this general idea that as your little samples, as the size of the samples increases, the standard deviation of the sample mean, which is our average for each of the little clusters, decreases. So basically, the bigger the sample, the smaller the standard deviation. Now usually, how do we make something smaller in math? It has a tendency to use division. So here's what we know. The averages roughly seem to stay the same. They're 2.46 for all of them, because the mean is still the mean regardless of how many the expected value, regardless of how many times you throw new numbers in. However, the standard deviation standard deviation of the sample mean takes your normal standard deviation and it divides it by the square root of n, where n is the number in your sample. So if you took your standard deviation and you divided it by the square root of 5 in the first problem, here would be dividing by the square root of 20. So let's check our sample here. A sample of 20. So x bar is 2.46, and our standard deviation according to the problem up above was 0.0045. So let's see. So our mu x bar is supposed to equal mu. Was our 2.46 equal to the expected mu in the original part of the problem? Yes. Now it says our standard deviation is supposed to equal this regular standard deviation in the problem divided by the square root of n. Now, the regular standard deviation in the problem was 0.02. Now let's divide that by the square root of 20. It's approximately, after putting it in the calculator, 0.00447, which rounds to 0.0045. So it does follow what we expect to occur. Now that we've done all of that, in the next video, we'll actually do some problems from start to finish instead of doing the setup.